This is problem number 6 of the International Math Olympiad in the year 2007. Let n be a positive integer. Consider set S that consists of triples x, y, and z, where x, y, and z belong to the set 0, 1, 2, 3, etc. up to n, and x plus y plus z is greater than 0 as a set of n plus 1 cubed minus 1 points of three-dimensional space. Determine the smallest possible number of planes, the union of which contains set S but does not include the triple 0, 0, 0. Well, the good news is that I have purchased a Samsung USB microphone, and hopefully the quality of sound in my videos will now improve. Let's examine the first case when n equals 0. In this case, set S is empty, since the three-dimensional point 0, 0, 0 does not belong to set S by definition. From this it follows that the number of planes that cover set S equals 0. The next interesting fact that is a real breakthrough in the solution of this problem is that for any given positive integer n, there exist 3n planes that cover all points of set S for this n. It's easy to prove. Recall that for each point in set S, the sum of coordinates of such point varies from 1 to 3n. That's why the planes that have equations of the form x plus y plus z equals k, where k varies from 1 to 3n, cover all points in this set for any given n. The cross-section of each such plane with three coordinate planes xy, xz, and yz is an equilateral triangle. All these planes are pairwise parallel, so they are distinct and cover all such points. If we prove that any number of planes that cover all points in set S is not less than 3n, the answer to the question of this problem is 3n. Let's consider any plane from the group of planes that cover all points from the set S. Any plane in three-dimensional space can be represented as a linear equation in the form ax plus by plus cz plus d equals 0, where at least one of the coefficients a, b, and c must be non-zero. Also, in our case, the freestanding coefficient d also must be non-zero, since if it were equal to 0, then such equation would include the point of origin 0, 0, 0, which is not allowed in this problem. If the number of these planes is k, then these k planes are graphs of k linear equations, shown on the diagram. Let's define a polynomial p of xyz that equals the product of all k of our linear equations. The degree of this polynomial is k, and this polynomial has value 0 or vanishes in all xyz points of set S. Now, if we prove that any polynomial that vanishes in all xyz points of set S has degree not less than 3n, that will prove that the number of linear polynomials, which is the same as number of planes, is not less than 3n, in which case the answer to the question of this problem would be 3n. Let's prove it by using induction. Let's start from a simple case when set S has only one dimension, for example x, that varies from 0 to 1, and two other dimensions, in this case y and z, are set to zeros, and exclude point 0, 0, 0. This set consists of only one point with coordinates 1, 0, 0. It's clear that the degree of any polynomial that vanishes in this point cannot be less than 1. An example of such polynomial is shown on the diagram. this polynomial vanishes in this point. We could have a polynomial with a higher degree than 1, but clearly cannot have a polynomial with degree less than 1. Now let's start increasing the dimensions of set S one at a time. And with each increase, we'll prove that the minimal degree of a polynomial that vanishes in all points of the next set S is increased by 1. In this case, the next set S consists of two variables, x and y, that vary from 0 to 1, and the third variable, z, is set to 0. And as always, the origin 0, 0, 0 is excluded. The new set S consists of 3 points, 1, 0, 0, 0, 1, 0, and 1, 1, 0. The degree of polynomials that vanish in all these 3 points is at least 2. We can easily prove that it cannot be a polynomial of degree 1 in two-dimensional plane, x and y. The graph of a linear polynomial in two-dimensional plane is a straight line. One line cannot include these 3 points. So we need as a minimum 2 lines, as is shown in the example on the diagram. The product of two linear polynomials has degree 2. The next step is when all 3 dimensions, x, y, and z, vary from 0 to 1. This is the case where number n mentioned in this problem equals 1. The degrees of polynomials p of x, y, z that vanish in all 7 points of this set S are not less than 3. Let's assume the opposite to prove it. In this case, when the opposite assumes polynomial of degree less than 3 in 3-dimensional space, it's not so easy to analyze it as it was with previous cases. What will help in this case is Little Bézout theorem. The Little Bézout theorem, or the polynomial remainder theorem, states that polynomial function f of x can be divided by a linear polynomial x minus r, and the remainder of this division is f of r, the value of the same function f in argument r. In particular, x minus r is a divisor of polynomial f of x, if and only if f of r equals 0. Now, this is brilliant. If we apply the Little Bézout theorem to the polynomial p of x, y, z, the first degree polynomial is x minus 1, because the highest value of x, y, or z in set S is 1. Since it's the same for x, y, and z, the first degree polynomial could also be y minus 1 or z minus 1. Our opposite assumption is that polynomial p has degree less than 3, from which it follows that polynomial q has degree less than 2. If we look at the values of polynomials p in those points that belong to the current set S, in which variable x is not equal 1, then by definition polynomials p in both sides of the equation vanish in these points, from which it follows that polynomial q also vanishes in all these points. And by our proven base, in which two variables of x, y, and z vary from 0 to 1, and the third variable is set to 0, the degree of polynomial q is not less than 2. In general case, the degree of polynomial q is not less than the sum of highest allowed values of variables x, y, and z minus 1. This is contradiction. It proves that if the highest allowed values of all 3 variables x, y, and z are equal, and each of them is equal to n, then any polynomial that vanishes in all points of the corresponding set S are not less than 3n, which proves that the answer to the question of this problem is 3n. One additional note. We could also use the little Bezout theorem to prove that all polynomials that vanish in the set S where variables x and y vary from 0 to 1 and variable z is set to 0 have degree no less than 2. In this case, the polynomial of the first degree could still be x minus 1, and polynomial q would vanish in only one point, x equals 0, y equals 1, and z equals 0. By the base case, for such set with only one point, this polynomial must have degree at least 1. For example, this polynomial can be y minus 1. And so the product x minus 1 times y minus 1 has degree 2. This completes the solution of this problem.